Now, we are going to look at the carrier motion at thermal equilibrium. Even though there's no net current flowing at thermal equilibrium, the carriers are not stationary but moving around under the influence of various forces. I'll only explain what is going on in the conduction band. But the same explanation also applies to holes in the valence band by changing the charge polarity. In traditional wheel, there are more electrons on the n side so that they move to the p side by diffusion. Due to the electric field in the depletion region, some of these electrons are driven back to the n side by drift, which is indicated by the slope in the band diagram. Thermal equilibrium is achieved when the drift current is equal to the diffusion current. This explanation is a bit weak and confusing. We will take a closer look at the carrier motion. There are many electrons on the n side of the p-n junction, but most of these electrons are below the energy level EC-P0. The notation indicates that it is the EC on the p side at thermal equilibrium. The n-side electrons below EC-P0 will not be able to move to the p side due to the existence of the potential barrier in the p-n junction. So, only electrons with energy higher than EC-P0 can freely move across the two sides of the diode. The number of carriers above EC-P0 on the p side is just NP0, as we derived before. The carrier distribution on the n side is governed by the Fermi-Dirac statistic. At thermal equilibrium, the Fermi levels on the n side and p side align, and the energy difference between EC-P0 and the Fermi level is the same on the n side and p side. As the Fermi level sort of represents the water table explained before, the carrier concentration above EC-P0 is the same on both the n side and p side of the junction. That is, the electron concentration on the n side above the energy level EC-P0 is also NP0. There are more electrons on the n side, but most of them are below EC-P0, and they are not counted when considering electron motion across the junction. Therefore, there is no net movement of electrons to any side of the junction, and this results in zero net current.